Can everyone see my screen?
Yeah, I can.
Okay, good. So I think I will make a start. First of all, welcome and thank you for joining today, this third session. Um, I hope that you guys manage to do your exercise. So this the second of the last session, and um, whether you manage to find the solution before I send it out the solution or not. I mean, I hope that at the end of the day, with the solution, you guys are now in the well in a better position to understand better how to use Python in Plaxis, at least to manipulate the input program. Okay, if you wanted to set up a model, or if you just want to create a large number of elements that otherwise you have to do manually or with commands, but without any logical operations. And now the goal of this session, as we discussed last time, is going to be more focused now on output. Okay, this session is going to be exclusively main aim on the result extraction. And in the next 2 weeks, in the last session, the idea is to go back to the results that we extract today. And we're going to do a little bit of post processing to generate plots or to generate tables in a different ways. Okay, so for this exercise, I hope that you all receive the email from Palak with session 3 exercise. Again, it's going to be the same format. It's just partial part of the code that you received, and the idea is after this session, after this presentation, you guys trying to fill the missing gaps of the codes. And as always, next week I will send out the solution for today's exercise. Okay, so as a starting point, let's go back to the model that we created 2 weeks ago. So this is going to be our starting point. Uh, let's assuming that we have the model already created. So this is the if you all recall last session, what we tried to replicate automatically was a pile raft with a pile layout with different pile diameters and lengths. I tried to run and mesh. And now the idea is to use scripting in order to extract the results of this model for different stage, but also for different for all the piles. Okay, and the idea is at the end of the day, what we want to get is the results presented, let's say, in Excel file in a tablet format, without any post processing, just simple extraction of all the results per pile, not only on the top, but across the entire length of the pile. Okay. How do you do this? I mean, that's one of the things we're going to extract. The second thing is, so that will one, it will be the piles. And the second will be like we're going to define a typical cross sections across the raft, and we want to extract some typical structural results across the raft. And we are also going to do this with Python. Okay. How do you do this manually? I mean, for those who are not so 100% familiar with the process of Plaxis 3D, I mean, the way we have to do to extract results in Plaxis is to open the output, which I'm opening now. Okay, it's still this one. Just close this one here. Open again. Okay, so we're going to see the results, but now let's say if I want I just cite the soil, let's say, and oops, that's the German. Sorry. Uh, so we have here the piles. The typical workflow manually, what you do is you just have to go to one of the piles one by one, and in theory, what you see, you can only see the results per phase, per pile. Or I mean, you can see for all the other piles. You could say that if you want, you could go here and say, well, I want to select all these piles, right? If you want, but then it's difficult from here. First of all, it's difficult to understand. It's not so straightforward at the beginning to understand because you have a lot of overlap of the plots. And even if you go to the table results, the data is not sorted. So it's difficult to understand from this table. If you look at this table, it's difficult to understand what is pile 1, what is pile 2, what is pile 10. So the only way to do this in an efficient way is to go to one by one and extract and copy paste. So you can imagine that if we have 80 piles, right? We have 80 piles for how many phases? At least we let's ignore the pile installation effect, the pile installation 3 phases. So 80 piles multiplied by 3. So you can already imagine how many times you have to do this manually if you want to extract results for all the piles. Okay, so but we are not going to do this, fortunately. Well, what we are going to do is a script that can do that automatically. And the second thing, like I was saying, is the raft. The raft is basically, I mean, also it's not a very difficult workaround, but as you can imagine, if you have to extract results in a lot of interfaces, let's say, sorry, a lot of plates. So, for example, if I want to have here the raft, right, and these are my results, and now I want, so let's say, two cross sections, one that pass here and the other one pass here, okay, perpendicular to the plates. So if I just do this, create a line for one of them. Now I have the results, and then I have to select the results I want. And then in principle, if you go to the tabular results here, you already have all the results. I mean, you don't need to extract the results one by one. You can extract in one go. But again, if it is just two sections, it's not the end of the world. But if it is a big project, you might want to find a more efficient way to do it. So now that we already explore how to do this manually, just for us to have a little bit of understanding why we are doing this in the first place, let's now move on to the script. So you probably have a script similar to this one that I'm showing you in a moment. As a first starting point, which is important, we import everything that we need to let's say we have to initialize the first models. Okay, the models that we require to do the operations. So one of them is going to be pandas. Okay, the other one is math. Okay, so we already talked about this in the last session, and also this one you don't have, but these are the piece of codes that which contains the missing the codes that are not present in your scripts. So in order for me to be able to run this in this session without typing, but the idea is that in 2 weeks I will provide the full script in which it has all the code there. Okay, we have our boilerplate. Okay, which we already discussed. We define the ports, the passwords, and now the first step is to define, let's say, the algorithm that will extract the results for all the piles for each key stages that we specify that we want to extract the results. Okay, and the algorithm, I took the liberty to come up with this flow chart to help you guys to understand a little bit the process instead of you trying to understand the code here. It's in a visual way, trying to understand at least the logic behind it. So the strategy we are going to use is, first of all, we are going to create empty data frame with pandas. Okay. Second, we have to define a Python list that contain all the phases we want to extract. Okay, so in this case, if I go back to the model, I'm saying that I want to extract in the raft construction, short term and long term. I'm not sure if I put also the pile. Yeah, it's just statute exactly. So we want only to extract on this tree. So that's going to be defined. So first of all, the definition of the creation of the empty data frame is going to be here. Okay, we have here the definition. Actually, we also have here. I can show you a demonstration of this. So let's first run these ones. Okay, so let me just run this. Now run the boilerplate. Okay, so let me just close this one in the meantime, just to have already some lines of code. Actually, what I'm going to do, because I was running the script before, let me just start from scratch this. Just a moment. trying to restart this. Okay. Well, okay, it's already restart. Okay, so let's start to run this one, this, and this one. Okay. Now it's doing the connection to Plaxis. So maybe it's going to take a bit of while. Yep. Okay. Then now let's here I'm defining the Python list first, but it doesn't matter if we create the data frame or before or after. It's quite irrelevant. But like I said, stage 2 is stage 4. Keep in mind, pay attention that I'm not defining a Plaxis object here, and what I'm defining is in terms of strings, because if you recall last time, we call this stage 2 at stage underscore 2, stage underscore 3, and stage underscore 4. There will be a get attribute later that will try to make association based on this string. It will find the associate Plaxis global object that is associated to the face, which we will see later. Okay. And let me just initialize this. Now, what I'm going to do is, first step, let's open the output. So we have go to stage. Go to stage means that, as you already saw in the last stage, move to stage construction on Plaxis. So I even going to move it here to, so let me see if I just can put this in a way that we can see this operating at the same time. Okay. So go to stage, and then we ask to view the phases on initial phase, let's say. Let's start, okay? And you're going to see again, pay attention again, the similarity with the code of the Python code with the Plaxis command. So you see that go to stage and view initial. So it's quite similar. These commands, I mean, like again, if you know what is the Plaxis command that you want to run, to find the equivalent Python code to operate this, in most cases should be straightforward. Not always, but most of the cases it is. Okay. Now that we have this, I just wanted to let's create a data frame here. I mean, here is not associated with any variable, but in order to create an empty data frame, what you have to do is you have to call the object pandas and then data frame, and it's case sensitive. So you need to put capital D and F on the name, because if you don't put, the program doesn't run. So it's case sensitive. So if I do this, then you see that it generates this bit here, okay, which means that it's just a data frame that is empty, nothing else, okay. And if I put say A, so let's call this A. Now just now let's say if I call the variable A, it will give me this empty, and if I put type A, there you go. So this is a pandas data frame, which, and also if let's say what is the length of that data frame? It's going to be 0. It's empty. So how do I know it's here is empty? Because if I try to determine the length of that data frame, it will return 0 also. Okay. So okay. So before, so now that we already explored a little bit this part. Let's now see what is the loops behind this. As you can see, this is going to be consist by 2 loops. Okay, so it's going to be 2 loops, and it's going to be operated mainly on this part here. This 2.4 is just a function. Okay, it's the function that basically comprise this first loop here. Okay, so all the first loop logic operations is defined in this function, and the idea is we're going to run, let's say, this loop here, the second loop in the 2.5, which is going to iterate on a list phase. Okay, so we know that we're going to say, well, I want to run a loop on that list, the list of phases, and for each phase I want to run a certain actions. In one of them is to find out what is the Plaxis what is the global object that refers to that phase. Okay, and second is to run this function that's called extract pile results per phase, which is defined here. Okay, so the idea is of creating a function is to make the code tighter and to make cleaner and understandable. And also, it's a way that if I want to reuse this code later in the script or in another script, it's very easy for me to copy paste this and save this as an as a function or even a Python class. Okay. So basically then, so we are doing this. We are running this first lap, this first run. So we pick. Let's say what happens now is the first step of the first loop will be iterated on stage 2. Okay, so we are going to extract results on stage 2, and of course we go here to the loop, and we have, okay, this is, we start here, we obtain the object, and then we say, okay, we want to run that function, and now on that face. And just to give you an idea about these attributes, so if I put face list, that's the Python list, right? And then if I put the first index is stage 2, and now if I run just this part here, right? What it's going to give me is, so I put this as let me substitute this part with the string of the first list. There you go. So we know if I save now this to a variable called face, that variable face is going to contain the Plaxis object in output. And pay attention that this is in G underscore output. Before we were just working with global objects and server objects in input, and they still define here in the boilerplate. But now mainly we're just going to operate here in this area because we are just extracting results here. Okay. And I mean, how do I know this is phase 2? Where's this? No, sorry again. Yeah, how do I know this is this piece of code is phase 2? So if I put phase, let's say phase test. Let's call the variable test. Okay, and now if I put test underscore name. Oh, sorry. You see that is the case sensitive also here. I put test because now it's an object, and inside of that object I have attributes, and one of them is name. Okay, I put name, and then I put value, and there you go. That this Plaxis output object that we create based on the first list of the face underscore list refers to a Plaxis global output object that is called stage 2, and that's what we want. Okay, so let me just delete this. Now that we run this, and let's now a little bit explore more in detail about how this loop works exactly. So this function is called extract pile results underscore per underscore face underscore I, and accepts a variable called face underscore I. And then it's inside of this loop that we create the data frame. Create one. We already created the global data frame df all. We create outside this data frame is where we are going to store all the data. All the data we extract at the end, it will be saved inside of that data frame, but we need to create other data frames to store the results temporarily. In this case, we need to create a one that is called data frame that is called face, which is going to be the one that is going to store all the embedded beam results on that specific phase which we are iterating at the moment. In this case, it's going to save all the results at stage 2. Okay, and then at the end, when we finish to extract, we will merge this one with the global, with the one that stores everything. Okay, so it's basically is adding information, like every time you finish the iteration, it kind of copy paste the information to the other one. Okay, and it puts all this at the end of the data frame, so it concatenate. It's a Python function called concatenate that does that. Okay, so we create that data frame. Now we create the second loop inside, and the second loop is the one that's going to iterate for each embedded beam. Okay, because the goal is to extract results for each embedded beam. And what we are going to do is we're going to extract several results. Okay. Uh, we're going to extract the name. This one is going to iterate on the first embedded beam. It's going to iterate not only the first name, its first name, and again, keep in mind this one is not referring to the output; is referring to the input. The idea is because the reason I do this, and it was maybe I just forgot to say that before we start this, you will see that the script will move from stage construction to structure because I want to iterate from the objects of the embedded beam that are present in input. The reason I do this is because if I go into the stage construction, then if I go to the embedded beams now, let's say, which the embedded means, it's going to be, yeah, it's here. You see that the names, because these are cut object cutoffs. So these are results. These are objects resulted from the intersection with the soil and the structure. So the name. I mean, it's like if you have one, instead of having one element, if it is intersects with other layers, that element might be subdivided in different segments. So in order to make sure that I'm not picking sub elements of the same pile, I move to the structure, and then I know that if the first one in the list is any element of the embedded beam, it corresponds to the food pile. Okay, that's the only reason I do this. Okay, so we're going to iterate along the piles, and then not only we're going to extract the names, we're going to extract the coordinates, so you can see x, y, z. And the way to do this is so the name is it's very obvious how to do it. You have the pile object. So let me just give an example. Maybe it's easy. So if I do, let's say, if I extract the first element of the embedded beams, okay, that's an element, right? Now I go to name. If I put name and then value, we have embedded beam underscore one, right? But if you all recall it, last session we took the effort to name the piles with the correct names, if you all recall it. So if we go to the geometry lines, we call pile 1, pile 2, pile 3, which is what we want, because at the end of the day, I mean, I don't know what is embedded beam underscore 1 if or underscore 2, or what I know is the physical meaning of pile 1, pile 2, pile 3. Yeah, that's what I want. So what I can do is I can refer, if I have a feature, if I'm calling a feature, I can refer to the parent. The parent is the geometry element that generates that feature. So in this case, the embedded beam is a feature of a line. Therefore, if I put parent, what I'm going to get is a line, because now if I put type, we should see, maybe doesn't say here what's the type. But what I know is if I go to put name and now value, there we go. We have the name. So that's what we're going to extract in this first line. We're going to extract the pile name, and then we're going to extract the coordinates. Now the coordinates, the remaining results. This is the part that might not be so obvious at first, but once you understand, it's very easy to understand the process. So we are going to use this get results command. And my suggestion is you guys go, I mean, it's similar to the Python command, the Plaxis command for get results. So if I go get results, okay. And what is get results is generate a table with calculated results. So basically what that means is when I run this command and say I want to extract all the results for the x coordinates of that pile at that face. So this is the pile, this is the embedded beam, this is the face, and this is the type of result I want to extract, which is the x coordinate of the embedded beam at the nodes. What I'm going to get is not one value, but a table. And in this case, it's going to be more of a column, a vector, which contains all the x coordinates of the pile along its length. So what we're going to get basically is on pile 1, because it's a vertical pile, it's going to get the x coordinates of all the nodes of that pile, which is going to be the same. The only thing that in terms of geometry that change is just x, but you get the idea. So basically every time we run this, we don't get one value, but we already get all the results of the pile for that specific result that we are targeting at the moment. So we do this for the x, the y, the z, and part of the exercise, part of this exercise, the exercise, the challenge I give it to you guys to think about, and we'll present. I'll give you the solution next week. Is to try to replicate, knowing that this is how you do it for example, for X, Y, and Z. It's going to be very similar also with the other ones. Okay, so if we want to extract the results, vertical displacement, bending moments in both directions, M2, M3, shear forces and axial force, it's going to follow the same format. But part of the challenge is for you guys to figure out how to do it. My recommendation is go to the command reference, trying to get yourself familiarized with the get results, and also another thing that you can also do is have a look. So these get results you can see on the command reference, but go also to the output reference and try to see what are the type of results you can obtain from a embedded beam. So if you go here, you have a list of all the possible results you can extract. So it should not be very difficult to do it, but if I hope, but don't worry, if you are not able to do this, you'll get the full script next week. Okay. So assuming that we run this, so this is going to be this part. So it's going to be the extraction of the results, the settlement, the structure force in all the nodes in the embedded beam in that specific phase using this get result. Then, okay, we have all these columns. The information is like a bit not yet sorted out, but okay, it's there. It's like if you have different objects with different results inside. Now, the idea is to try to put everything in the same data frame and sort that information in order to make sure that the results are we sort this from the top of the ground to the low from the pallet to the toe. Okay, so how do we do that? Again, we do another loop inside in which we iterate these results. We say for every one of these objects vectors that we obtain, iterate, and the first position of each vector should correspond to the same node. So for example, if let's assume like let me just say this again. If we assume that the first node is the palette, then all the first elements of that column will correspond to that node, and so on. And if the last is the toe, it's going to be the toe. So we don't need to worry about the order in which this information is in each column. We know that each value at each index, they correspond to the same node. Okay, so if knowing that, then I can start to do some inter stuff here. For example, if I what I'm saying is by doing this first loop is I'm going to the first element of the column or the first line. Let's say if you imagine a code, if I go to the first line of all these columns, I extract the results and I say, okay, well, my vertical is going to be so of course I say for these variables inside of these columns. So vertical is going to be associated to PAL-UX, which is going to be the one that is the settlement. For example, this one is going to be the elevation, so it's going to be the third element here. Okay, so what I'm going to do is do some small processing in order to make sure that I can have this sorted out. So first thing here, what I'm doing is I'm changing the signal of the displacement, of the vertical displacement. I'm calling this a variable called settlement, but in this case, it's going to be settlement, but you could call it whatever you want, okay? I'm inverted the signal because all the results are going to be, because if it is a settlement, I want settlement to be positive because of sign convention. But let's say if settlement is positive, then I'm just multiply by -1, and I also multiply by 1000 to convert this from meters to millimeters. Okay, because the results in Plaxis are meters, and we want to work in millimeters, so we're already converting this to units. The moment and the shear force, for the purpose of this exercise, I assume that it's going to be the resultants of both actions in the horizontal plane. Okay, so I'm going to do the square root of the direction 2 and 3. Okay, so you can see this, and in order for you to do a square root of this, you have to use this math function, which is the one that we call here at the beginning. Okay, uh, without that you're not able to do square root, so you have to call this Python model in advance. Okay, and the way to do it is just math dot square root, which for you see that there's a bit similarity with Excel here, right? This is how you call in Excel also. So you will see that a lot of things in Python, when it comes to mathematical operations, you see that there's a bit of resemble to some mathematical operations you see in other commercial softwares you see out there. Okay, and then I'm putting here, let's say, a function in which I'm saying, well, if my actual force is in compression, which is in negative, some in Plaxis negative means compression and positive mean tension, then I'm saying, well, if I want to say that my ULS actual force is going to be factored by 1.4, then what I'm doing here is just multiply by 1.4. And again, the sign convention I want to use in my processing later is to assume that compression is positive and tension is negative. Okay, so it's opposite of Plaxis. So therefore, I'm multiplied by -1. Okay, so it's what I'm saying is if it is lower, if it is smaller, if it is negative, multiply by this factor. But otherwise, if it is positive, I want to use a different factor, 1.35. That's up to you guys what to want to use, but let's say for the purpose of this exercise, I choose 1.4 and 135. Okay, and again the same thing for the moment ULS and the shear force ULS is going to be the resultant multiplied by the factor. Okay, then after we have this, we have already our results somehow process with the right units, the right sign convention. It's time for us to put everything into the same data frame. The way I'm doing this is at the beginning, I create this empty dictionary, okay, which basically for each time, so basically what happens is for each line that process, it's going to save that set of information inside of a Python dictionary, which is referred to the key, which is elevation. Elevation is unique for each pile. It's a vertical pile. We don't assume that there are nodes with the same elevation. So I'm using the elevation as a is my sorting is the element of identification of the results. Okay, so I'm saying that okay, all these results that we extract for that line, they correspond to the node that is located at a certain elevation Z. Okay, now that we have this, so we do this, we run this loop, right, and then after we iterate all the lines of the vectors, then we will get at the end, what we're going to get is a dictionary which has different keys, and each key is for each elevation to do. So it's the results for each node, okay? And now the idea is to create a data frame, is to convert this dictionary into a data frame. And the way to do it is, and the reason I used a dictionary is because if you have your information sorted inside of a dictionary, then to transform this into a Panda data frame is very straightforward. You still use the same data frame function, but you pass the dictionary inside. You say you index when you ask, well, how you want to sort it out is in terms of index. You put as no, and you put as a transfer, to transpose. Okay, you put them to transport. If you use this line of code, then what you're going to get is now a data frame that each line corresponds the results for each node at different elevations. Okay, and okay, we create, but we are not yet done with this. What we have to do now is to we're going to reset the index. Okay, I want to reset all the index here. Okay, um, now I want to give names to the columns. Okay, because at the moment there's no names. It's just a data frame with values, but there's no headers in the columns. Okay, so now we can now start to have headers. Okay, and I put here the names, and I have to put this in order. So if I define pile name, phase name, elevation, displacement, and so on, I need to make sure that I'm naming in order, in the correct order. Okay, because this is going to identify the first column, second column, third column, so on. And now the next step is for you guys to figure out how to sort it out this. And to sort it out this, we're going to sort it out this in terms of elevation. So one of the columns is going to be the elevation. We want to sort this information to make sure that it's sorted from the ground to the toe level. And my suggestion is you can search on the pandas documentation how to do that. It's very straightforward. If you go to pandas and try to sort on Google data frame sort, you're going to be most certainly moved. You're going to be redirect straight to that line of documentation. Okay, so and then if you do this, then you just sort your data frame, and ideally at the end of this operation. So if we go back to the workflow, we are now in this part here. Now the next start is, okay, well, we extracted all the results from one pile. Now it's time for us to insert that data inside of the data frame of the face, which is the df underscore face, by using this pd dot concat. So that concatenate option, that basically you just make sure that you're adding more. So basically the way it works is you use the data frame face, which is going to be the target that the data frame we want to target, and which data frame we want to insert. So because these data frame for face now it's empty in the first element, so the results of this is going to be for the first file. When we reach to that stage of the first loop, the data frame underscore phase is going to be equal to df pile, but then later in the second phase is what is going to happen is going to once we finish the second phase, the second pile, this data frame is going to be consist by the information of data frame one, or the embedded being number one, and then the next row below is going to be the embedded being two, and so on and so on and so on until we reach the end of the embedded all the embedded beans. Okay, and of course we concatenate, and then there's this logical operation which we're going to the program is going to check. Okay, did we already iterate all the embedded beams? If yes, it moves on to the next phase, but no. If no, then it do all these loops. So basically what I'm saying here is that this loop is going for each phase, this loop is going to be repeated 80 times because it's for each pile. Okay, so as you can see, it's more or less, this is more or less the thinking, the logical thinking. And what I always recommend is, I mean, it's always a good idea that if you are trying to create something and you know what's the logical operation that you want to do, it's always good to create this kind of flow charts to to kind of help you to organize how you're going to set up your code. And in this case, you see that the code in general follows a little bit this philosophy. So now we for, let's say, for stage 2, is going to extract all the results here. And then once we extract all the results, all the results for all the piles, only then, let's say we go here and we concatenate this to all the results for that phase, which contains, so at the end, when we finish this extraction per phase, it should contain all the results for all the 80 files or that specific phase, and is going to concatenate into the data frame that will contain all the results. So as you can see, it's a loop inside of the loop, and then there's a third loop which is not represented here just for simplicity, but there's this third loop here which iterates the results for each node to make sure that we do the post processing and sorted out the information in the correct way, okay, and put in the right units. So yeah, I mean, basically then we concatenate, then we reset the index, and we save this in this data frame. So at the end of the day, you should get something like this. So let's just run this just very quickly. Okay, just now that let's just run the phase, and now if I run this one, right, you see that. You see what is happening here? All these lines that you're seeing here basically is these commands here. Okay, so it's like for each pile is running 1, 2, 3, then 4, 5, 6, 7, 8, 9 commands of get results for each file, and then once we get these results in terms of a column, then does the post processing, saves into the data frame of pile, okay, and then merge this to the one that is the face, moves on to the next pile until it reach all the piles, and only then emerge the data frame from the phase to the global one and move on to the next phase until we run out all the phases. So yep, it's now we are now in long term. So you see that it moves automatically the phases. Okay. So let's wait a second. Okay, should be almost there. And you can, as you can see, I mean, we see embedded beam underscore 57. I mean, in this case, might be past 57, but sometimes you might not. So it's important for us to extract the results on a light element and not on embedded beam. I mean, depends where you name the element, of course. But in this case, because we decided to put the physical name in a light element, then therefore I'm extracting the name of on a light element instead. Okay. Okay. So okay, we already ran this. Now, as you can see, I mean, we have a data frame. So let me just do this. You can see that the data frame now we have, it's already sorted. Okay, so it starts at the top of the elevation, top of the soil. We don't see all the results here because it's going to be you can see it has 7,000 rows. Okay, but as you can see, the results are already sorted out in terms of phase, in terms of elevation, and then we have all the results for the embedded beam. Okay, and the next step is to save this into an Excel file. Okay, so in order to, well, in this case, we're going to save this in a CSV file. Okay, so if I do now this, okay, and now if I go, it will generate something like this here, CSV, this file here, and now if I open, there you have it. You have all the results here, all the results from your Plaxis model, sorry, all the results for your embedded beams are all here. Okay, and of course, if you want to, let's say, if I want to filter this, just to make sure, let's say, sort and filter. Let's filter this. Let's say I want pile 1 at stage 2. Well, actually, we can see all the results here. You see that we have all the results of pile 1 for stage 2, stage 3, and stage 4. And as you can see, they are sorted by elevation. So you can see this, it goes from elevation 5. So just to recap, the elevation, if I go back here to the SUM model, You see that it starts at 5 and then it goes up to whatever pile, whatever pile we want. Okay. I think the only thing is missing here, but I can make sure that in a complete code is there. That now I realize that is missing is the diameter. Would be nice to have a column with the diameter, which is also easy to do. To be honest, I can show you how to do it very easily. So if we have this now, diameter should be. Um, yeah, because we have to move maybe here, I guess. Embedded beam. I hope that is this. I have to see now where it is. Or diameter. Okay. Sometimes you have to use the right name, but I think diameter. Okay, I will see later because I think on this one I'm not sure why it's not working now, but I think why is that happening here? This let me just wait. So if you don't know, you can go pile. Let's say embedded beam. I can use echo embedded beam. If I don't recall the name, the exact name, then I can do _1. Okay, we have this, and then we can go to material. I think. Yeah, that was what was missing. As you can see, this is a prime example of you want to do something, but you don't recall. Then you can go to Plaxis. Okay, well, if that's the way you're doing, then I'm just go to material. Yep, that's correct. Now I go to the material, and then diameter. There's a number, and then put value. There you go. This is 750 millimeter pile, the first pile. So we could also put here, if we wanted on to have on this final outcome, a column with the diameter following the same approach. Okay. So yeah, that's the first step, piles. Now the second step is going to be on extract the raft results in means of generated cross sections. And here we have the flow chart. I mean, you see that in the sense it's quite similar to this one. It's with some there's some difference, but the idea is almost the same. You create. So what we're going to do is we're going to create an empty data frame that will store all the results. We have a dictionary. We're going to have this dictionary that contains. No, sorry, the dictionary is this one. Sorry, it's this one, which basically will define the coordinates of the cross section. So we're going to call, if we say that this is, let's say, sorry, if we say that this is north, south, east, and west, then this say so we want a cross section that goes along the y-axis, and the other one is going to across the x the x axis. Okay, then fine. Then I'm defining here what are the coordinates of this cross section, and yeah, what is the name? Okay, and also we have here what we have here in terms of string is saying that at some point I want to, in the same way I did for the embedded beams, that I have to sort it out in terms of elevation. Here what I'm saying is that okay, if I'm doing a cross section that goes along the y-axis, then I want to sort the information in terms of y coordinates, and the other one is in terms of x, obviously. Okay, and we have the face list again. Um, then what we're going to do now, first of all, we have to create a structure plot based on the coordinates that we define here in the dictionary. Okay. You're going to see that we're going to see that if we go, let's say, yeah, we go like this, okay? So let's just close this again. Oh, just open again. The reason I close is just to delete the other ones, just not to have other things open in the background. Okay, view phase 3. We create this one, and what is A? Let's say A is going to be again. It's the same thing as the phases, right? So in the same way, we have to figure out what is the Plaxis object for the phases. We also have to do the same thing for the rafts. Okay, so we know that the raft calls. So what we know in terms of the raft is we know in advance that these rafts call in structure. When we move to structure mode, this call main underscore raft underscore surface, and the other one calls core underscore raft surface. Okay, so oh, actually, this is not my mistake. This is not in structure mode. This is everything here is on the green mode. It's on the stage mode. Okay, so that's why it has this underscore one, because on the stage mode, then we know that this one is going to call the same name as the structure mode, but it's going to have this underscore one because it's going to be what we are calling is not the full raft, but just the cutoff, the intersect part of that raft, which is it's going to be only this part, and the core is only going to be that one. Okay, because in the structure mode, this raft is all this surface, and when we run the analysis, that's what we're going to have is going to have this intersection happening. Okay. Okay. So where were we? Yes, base. Same thing as in Beam, nothing new here. And now what we want to do is let's explore a little bit this structure plot, because when what we're going to do is we're going to generate a plot showing what we are seeing here with structure plot is the same thing as when we go to here, and this is the same action of, let's say, let me just ID this. You know, in Plaxis, when you want to visualize results in a structure element and you just select like this and then double click, is the same thing. What you're running is a structure plot command. It doesn't appear. Unfortunately, it doesn't appear, but basically that's what they do. So what we're going to tell here is, okay, we know all the elements are called in output. Now let's see the structure results of these elements. So let me just run again, just to make sure that everything is run here. Okay. So I do this, and then I pass here the list with the list that contains already. So A is the list of these Plaxis objects in output. Then I just run this, and you see it already generates the plot, the structural plot of the raft of the elements that I selected, which is the outer raft and the core. Okay. Okay. So that's what we do. We generate this, create this. This column plate list, right? Then, of course, it's going to be the same thing again. We're going to create a function. Now, instead of being extract pile results, it's going to be extract plate results per phase. It's going to be the same philosophy, okay? The same philosophy we got that of use get results, and then, so let me just maximize this to be easy. So we're going to do the same thing. We have to create an empty data frame just to store the results on that phase, okay? And then we the other thing we have to do is now, because we have this, but we said that we want the cross section, right? So we want the cross section. Sorry, we wanted the cross section. So the way we do this in cross section is if we want to do like this. I mean, we just do that, and you see the command line. The command line now is called cross section plot. Okay, and then you have here you have the coordinates. So these are the coordinates that we defined before. Okay, here are going to be used to generate that cross section. Okay, that's what is going to happen. And just 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 to note something. If you run the structure plot with Python, then appears in the command line. But when you do this via graphical interface, it doesn't appear, which is a kind of interest behavior. Okay. So yeah, basically that once we have the plot, then it's the same workaround, more or less similar with the one that we did for the piles. Then we extract the coordinates for each node of the plot of the cross section, x, y, z. Again, this is part of the challenge for you guys also. So what I would say is we already explored the get results, but then what you have to do now, you have to go to the command lines, and I mean, if the same way you have on the reference, you have something for the embedded beams, you also have for plates. Yeah. So if you want to extract, let's say, um, actual force in normal force in the direction one. Don't forget that in plate we have two actual direction. One is in x1, which is the normal one, and the other one is going to be two. Usually is used as a hoop stress, hoop force. In this case, if you have a circle, this is more relevant if you have let's say a circle shot or something like that. So yeah, you have that. That's one thing. That's one thing, and then another thing that it's worth to keep in mind is um, you see that it's very similar. You have to refer to now instead of being get results. So before it was called get results, it was getting results on the main plot, that on the global plot, let's say. But now you only want to get results on cross section. So it needs to be get cross section results, which has the same structure as the other one. Okay. The only difference is now um, where you are the object you want to extend. In this case, you were telling I want to extract results on a certain element. Now you have to specify which plot you want to extract the results. And the tip I gave you is that every time you generate a plot in output, you generate a plot, and there's an object called plots. Okay. Sorry. Wait. Echo plot. So you see that if you do echo plots, it's a plot list called plots, and then what you have, you see that the first one in position is plot underscore one, plus, and then the second one is plot underscore two, and the last one is plot underscore three. Usually, the last element is the latest plot that you generated, because this was the latest one. Okay, therefore this one is going to be saved in position in the position two, but you don't need to know exactly what position you are safe. If you the good thing about this list is the same way you can put index it with positive numbers, you can put it with negative numbers. If you put -1, it means that we want to access the last element of that list. So that's what we're going to do. We don't know in which position this plot is located, but we know that it's the latest one. So we put here -1, so we refer to the last generated plot at the phase that we are extracting results at the moment, and what type of results we want to extract in terms of a column. Okay, so we do for X, Y, Z. Part of the exercise for you guys, like I said, is for the remaining results, and then it's the same. It's more or less the same philosophy. Then you save this inside of a temporary, let's say. So we stack this. So for each raft, we save this inside of a temporary data frame called data frame raft. Once we extract and sorted out that information, we convert this to the right units in signals. Then we save. After we finish to extract all the results of the rafts, we pass that information to the other temporary data frame, which is data frame face, and then it's going to ask the question, okay, did we already so did all the sorry did the 6 sections, just to make sure, is yeah, did we because basically what we are doing is for each phase, we are extracting results for each one of the sections, right? So phase two is going to be phase two, go to first cross section, a second one. Then he's going to ask the question, okay, did we already iterate all the cross sections? If yes, he moves to the next phase. If not, continues to the next section until we run out of all the section inside of this dictionary here. Okay, and then of course it's again. Then we go to the next phase, and the loop repeats. And as you can see, is a loop inside of the loop. And then once we have all the results extract for all the sections and for all the phases, then it's time to save this to the final data frame and then save this as a CSV file. Okay, so let me just now that I explain a little bit how this is work, let me just run this. I'm just run this one by one just to make sure that I'm running everything. Okay, so running the function, it's important. It need to be saved in the memory, the function. And now it's in the same way, you see that the code, you will see that there are, in terms of structure, is the same structure that we use for the embedded bin, but for different purpose, of course. Now, if I do this, so let's just move here. Let me just close these ones. So just to make sure that we are not, maybe it's better just to start from, yeah, let me start from here. So start from here, then run this, run that. I don't need to run the other ones because I already ran. So let's run this one. It should be fine. Oh, let me. It's better. Maybe I've skipped something. I might have jumped one of the commands. So if I just do run below, it should be fine. Okay, you see? Oh, extracting all the results. And then it moves. Once we've extract all the cross-section results for each phase, then it moves to the next phase. And I think it's already done. Should be done. Yeah. And as you can see, then you have the results here. So we have the results sorted out in terms X, Y, and Z. And of course, depending if it is one cross section or the other, the information is going to be sorted in different ways because the information is stated here in the dictionary, and at some point we have to tell the sorting to sort to as per this one, okay? And then we have the results here. At the end, we just save this in a data frame, okay? Sorry, we save this in a CSV file, which is going to be saved here, okay? And yeah, as you can see, we have a total of how many lines? 411 lines, which you can see that it's all these results, everything coordinated in different lines. Okay, so let me just filter this. Okay, now if I want to see all the results for the one of the cross sections, this one, right? There you have it. And these are all the results for that cross section for different phases. And then of course I can say okay. The other thing I forgot to say is on this one we only extract results on stage 3 and 4 because I don't care about the raft construction from a purpose of actions. It's just the construction is just switching place the raft. So I'm just interested to analyze the results in short term and long term. Okay, so it's these two phases. So yes, basically it's that, and then we have here the vertical displacement already converted into millimeters. Bending moments. We have here the bending moments here, and just okay. Yep. So that's pretty much that. I mean, of course, this is not the end of the story because what we did here today was just extract results, okay, from Plaxis, which is went to Plaxis and basically say, okay, I want to extract these results and save this in a data in an Excel file. I don't care about organization. I don't care all the information. I mean, we care about the information is sorted, but we are not yet generated something meaningful in a way that I can have a look and see plots. Okay, that's going to be the next section. That in the next section, what we're going to do is we're going to use this information that we save in the CSV files, and we're going to use this as our starting point to start to generate plots in Python. So yeah, I mean that was everything. Um, Not sure if anyone has any question, any doubts that want to ask.
I don't have any at the moment. Thank you very much. Does anyone have any question?
Yeah, I just want to ask, is there any possibility of using Python to check the critical values and
The critical
the
value,
outputs?
you mean the maximum values?
Yes, the maximum.
Yes, it is. It is. It is. We can explore this in the next phase. It's part of the processing, but what we can do is, for example, you want to know what is the maximum value, for example, for one of these piles, right? For example, let's
Yes.
go for the piles. For example, like what I can do is I can filter the same way I can filter the information here in Python, in Excel. So in Excel, I can create filters and say, well, just show me this information. I can do this something similar in Python, okay? And then once I filter the information, I can use a function called max or minimum and obtain the maximum. So you can do that, yeah. Let me see if I can do this very quickly. So if I call this mass one, and then let's say pal one. Let's could be pal one, let's say. So it's going to be df all. So it's going to be pal name. I'm just putting here, see if I can put this in a very quick way. So it's going to be equal to pal one. So you're going now to start to appreciate there, but yeah, because it's not the same name. Or is case sensitive? Oh, sorry. I mean, as you can see, to filter the information, you don't filter with just one command. You have to kind of do a logical operation. But so because I know why. Because the DFL wall is now called this one. But yeah, but let's do on this one. Sorry, let's do it because I wanted to do on the piles, but because we are using the same variables, it doesn't have a column called pile. So let's do on this one just to be simple. So you say that you want, let's say on section, I don't know, section, and then let's filter the information in terms of section north and south, right? Okay. Now what we're going to do is we create a mask that basically, if I now run this mask here, mask one, is going to produce a series, pandas data frame series, in which is constituted by Boolean operators, true and false. So what it's going to say is, well, the first line, the section column contains this value, true. Yeah, and false if it doesn't contain this value. So therefore, if I create the mask and now I call df all mask one, it's only going to show the results for the north and south section. But I can do more filter if I want. We say that we want the critical. You said you want the critical value. Let's say critical value at long term. Okay, then I can create another mask, but this time I'm going to create another mask for DFall. Let's say what's the name of this? Face underscore I, and it's going to be. I want to filter all the information that is stage 4. Okay, fine. Now, if I call this mask 1 and mask 2, Here we go. Here, what we have is 106 a data frame with 106 rows that contains only the results of the north and south section at phase 4. Now that we know this, what we can do is I can go, let's say, vertical displacement. Let's say I can only select if I want the vertical display. Oh, sorry. Sorry, for some reason my Control C doesn't work well. Ah, there you go. If I just select the column, I get a series here, okay? And the series says, well, here's the series for all the displacement. And now if I want to see what's the maximum value, here you go. The maximum settlement we get is 13 millimeters. But if you want, you can even know where it is. But for that, you require another set of logic operations to do that. But just to give you an idea that what in Excel is straightforward. I mean, it's very straightforward. In Excel, I will just go here. It's visual. I can see, and I mean, I could go here, say, or north. Stage 4. And then I know that, okay, where's the maximum value? It's going to be 13. Well, actually, it's not the maximum. It should be the minimum because this is negative values. So my apologies. So it should be minimal, actually. Minimum. Minus 17. So minus 17 with your 17. And you could see from expression where exactly is this location. But if you want to Python to tell you, okay, it's minus 17 at this location, you can also do that. But it requires other set of commands that now we don't have a lot of time to explore, but we can explore in the next session.
Thank you so much. Very interesting.
Yes, Omar.
Hi, Francisco.
Hello?
Thank you for your efforts. I do appreciate them much. I just wondered if you have shared the full script of the session 2 with us, as I think I did not receive it.
Okay. I think Palak, she sent the email to everyone. And Palak, I think you put the script there, right?
I'm not sure he did so, as I received the one we received before session 2. I received it twice.
Yeah, I mean, I mean, she sent the email when she sent the email, I got the copy, but I think we can, I can check with Palak for her to send again. Okay. No, if anyone didn't receive, please let either Arabelle or Palak know so they can share that with you guys.
Yeah. I
Okay.
will check with Palak as well. Thank you.
Okay. Thank you, Arabelle, and thank you, Francisco, again.
Yeah, thank you for your time again, Francisco. Yep, let's speak in 2 weeks then.
Yep, and we will see in 2 weeks, and I think next week we can well, the complete solution of this exercise will be shared to you guys.
Perfect.
But what I would say is try to see if you can do it yourself, because that's how in these things with Python and scripting, you learn with other people code, but you also learn by see other people questions, and sometimes you'll be surprised that, for example, for the sorting, what I can say is if you try to search on Google how to sort a data frame, you will see that not only you're going to find documentation, but you're also going to find people asking the question and people giving explaining how to do it.
Mm. So yeah, if anyone has any question, please ask. Otherwise, yeah, let's see each other in 2 weeks.
Okay.
Thank you. Thank you.
See you all, guys.
Bye.
Bye-bye.
Bye.
Thanks.